So in today's lecture, we will be continuing with our discussion about the Kalman filter, and we will see also some extension how to implement the Kalman filter for nonlinear systems. So on last week's lecture, I have promised at the end to show you some demo how to use the Kalman filter, for example, for a drone. So what we will be doing is that we will measure the acceleration with an accelerometer, and we will try to use the Kalman filter to estimate the position and speed just by using the measurement of this accelerometer. So it's like a simplified example, but it will show us that the Kalman filter is quite able to estimate those values only by measuring one variable. So if we study the problem, let's say we want to have a state vector that will represent the position, speed, and acceleration. So and we want to do this in 3D, so we will have 3 coordinates for each variable. So the space vector will look like this: x, y, and z. Here this is the position. Here with the 1 dot we have the speed, and with 2 dots we have the acceleration. And we measure actually only the acceleration, so we measure only this, and the other variables will be estimated. And we will assume that the motion of our object is linear motion with acceleration. So that's the motion type that we have done on last week. So we've done that first on 1D only. So for every coordinate, the equation will look like this: the current position will depend on the initial position, will depend on speed, and then it will depend on acceleration. And we will now generalize this case into 3 coordinates. So what we will do is that we will create the matrix A that describes the dynamic behavior of the system, and you can see the matrix A over here. It looks complicated, but it's actually very simple. You can see that for example, if I want to calculate position here, I take x, and x equals to 1 times this, which is the previous position, plus delta t times this, which is the previous speed, plus this term times x with 2 dots, which is the acceleration. So for every axis, this is exactly the same equation as we have seen in the 1D case last week. For example, for y coordinate, we see that this is 1 times yk minus 1, so this is the previous position, plus delta t times yk minus 1 dot, plus this is the acceleration. This is the constant related to the acceleration times this term, yk with 2 dots. And so for position, it's the same. For speed, we can see that for speed, this line here begins. So we have 1 times previous speed, which is xk plus delta t, and so on. If you would like to study more how this matrix was created, then this idea is based on this website. So like this, we can create quite simply the matrices that we need for the Kalman filter. And by creating the matrix A, we are saying what will be the dynamic behavior of our system. So now let me go to MATLAB, and I will show you how this is actually implemented in MATLAB. You have all those examples in Moodle, so you can take a look on your own. If you would like to run it at home, you need to get rid of this first section that actually reads the data from the Arduino. Because my example is built in such a way that I read data from the Arduino board, which has accelerometer, magnetometer, gyroscope and other sensors. I read them through the serial line, which is done here, and then I use this data to calculate in real time the output of the Kalman filter. So if you don't have the Arduino board, you will just erase this, and maybe you can replace those vectors with some constant or with some random numbers, maybe some constant signal with noise. That's how we could do it as well. So in my code, I first work with the serial line. So I read the data. Then this cycle, this is actually just to read the data from a line that is being supplied by the Arduino. So I read 3 numbers that correspond to acceleration. I read 3 numbers that correspond to angular velocity, which is measured by the gyroscope. Then I have a temperature sensor, which I don't need right now. And then I have a magnetometer, which I don't need right now as well. And then I will use the same algorithm that we discussed like 1 or 2 weeks ago, that will calculate the roll, pitch and yaw of the drone. So I will get some estimate of my angle, what is the correct orientation of the drone. So if you don't have the Arduino, you can replace all this for loop with some constant signals. And then I go on to the section where I actually do the Kalman filtering. The reason why this is split into 2 cycles is that this allows me to run the Kalman filter. Well, I will run it anyway, sample by sample, but I'm not limited on getting the samples directly from the Arduino. Of course, if you would like to do the real application, you would sample the data from the sensors in your microprocessor, you would calculate the Kalman filter, and then you will calculate some control action based on the output of this Kalman filter. So in a real code, this would run in a single loop. And here I have a section about the Kalman filter. We have seen when we have created the equations that actually the coefficients of the matrix A will depend on the sampling time. So I have set here the sampling time to 100 milliseconds, which by the way for a real drone would be too slow. So for a real drone you would need something like maybe 1 millisecond or maybe 0.5 milliseconds, roughly in the order of milliseconds. But here I'm limited with the ability of the serial line to actually transfer the data. Here I'm defining the matrix A, and the matrix A, it's exactly what you have seen in my slide. So here is the format. So wherever there is 1, I'm multiplying the value with the state vector directly with this value. So here we see 1 times, and this would correspond to the speed. Here we have delta t, which would correspond to the velocity, and here we have the acceleration in their corresponding axis. So the whole first line corresponds to the x coordinate, the second line corresponds to the y coordinate, and so on. So and then I'm defining the initial estimate of my state vector, and you see that I'm defining initially that all is 0. So all zeros is my estimate. I estimate 0 position, 0 speed, 0 acceleration. So I'm moving from standstill. And then I need to define the measurement matrix, the matrix C that we have discussed last week. And in this matrix, I'm sorry, I'm actually showing you a wrong example, as I see. So it should be this example, which is exactly the same. Only now I noticed that in the matrix C I have some additional numbers. So here in the matrix C, we are defining what variables do we actually measure. And you can see that I measure the last 3 columns, which if I go back to my state vector, here the last 3 columns here, they correspond to the 3 accelerations. So by putting 1s in the matrix C at those positions, I'm saying I measure this acceleration with an accelerometer, and I do not measure the other variables, so that I need to estimate them in the Kalman filter. So that's what's defined here. And actually in the other example that I showed, we've seen that we have a larger matrix, and this will be the next example that I will show you. And then I will just make an estimate of some variable b, which in my case I do not estimate any power from the motor, so I do not have anything in the matrix B. And I make some estimate of my covariance matrices, which we will see today also how to make this estimation. And then it's all the way go to the Kalman filter. So I make a prediction based on what I know about my system, and I calculate some new predicted state that will correspond to my model, and I calculated the predicted process covariance matrix. Then I calculate the Kalman gain. We have seen all those equations in previous lecture, and now it's time to update the measured vector x, the measured state vector, with the measured value. So I will update it with the measured acceleration. And since I do not measure the position and speed, here you can see I am putting zeros. So this 3 zeros corresponds to position, and these 3 zeros correspond to speed, and this is a vector of 3 values that correspond to the measured acceleration. And then I measure, I calculate what is the state estimate based on those measurements. So I use the predicted value, I use the Kalman gain, and I use the difference between the previous estimation and the actual measurement. And I simply save this as some new state. In this variable I'm saving the values because I would like to see the value of the matrix in the memory, so I have access to the data. And that's it. And then at the end, when this Kalman filtering is finished, we will see the result in a chart. So what I will get is a chart like this. Remember now that we have been working only with 3 coordinates. So what we see here is only the acceleration. The red symbols here, that's my estimation of my acceleration in angle x. Actually, when I was doing this experiment, it was standing still on a table. So when you run the algorithm, you are expecting to have all constant values. So you can see here this is the measured value, for example, for the Z coordinate. Here I'm having the same data, of course plus minus some small noise, and I'm expecting that it will be all the same value during the whole measurement, because I did not change anything, I did not move the device. And we can see how the Kalman filter will adapt. So after about 5 samples I'm quite near my measured value, and then it follows the measured value quite nicely. And we can see the same effect for the other coordinate. It starts from my initial estimate, which was 0 for all the axes, and then after a few samples, here it's even faster because the acceleration is near 0. It will follow this acceleration. By the way, here you can see that I did not have the accelerometer calibrated, because I am expecting then when it's staying still on some table, for example, then if it's calibrated, it should measure 9.81 meters per second squared. So here it's showing me 12 point something. So this is telling me that the accelerometer is not calibrated, and if I would like to calibrate it to get real data, I would need to measure it when it's standing still, and then divide it by the value to get the real acceleration that I expect, so 9.81. But for the purpose of Kalman filter, it doesn't matter at all if it's calibrated or not. We see simply how well this is able to follow the constant value. And how can I improve this algorithm? How can I improve the orientation calculation? Well, I will show you a second demo. Now it will be including some eventual movement, because here I did not change anything, so okay, it estimated the correct value, but what happens if I change something? So for this I have made a more complicated algorithm. I am now using the accelerometer to get the acceleration. I'm using the gyroscope to get the angular velocity, so it's speed of rotation against all 3 axes. And I'm combining this together with the magnetometer, which gets me what is north, where is north going. And I want to calculate the position, I want to calculate the speed, and of course I want to make an estimate of all those variables. So now I have extended my state vector. You can see now how long it is, how many variables do I have. This x, y, z is the position, this with the dot is the speed, this is the acceleration, so I measure this. I want also to have an estimation about or rotational speed, so this is those 3 angles, and here this is the angular speed, which is actually measured with the gyroscope, and this is the angular acceleration, which is not measured. So what do I measure? Well, I actually measure the acceleration here with the accelerometer, and I measure the angular velocity here with the gyroscope, and I use the magnetometer to combine the info with the accelerometer, as we've seen about a week ago. So I have also the orientation. The data from the accelerometer with the magnetometer to get the north, and this can improve us the info from about the position. So although the magnetometer is actually not in this state vector, but it could be, we will still use its info. Now I will not show here how the matrix A will look like. If you would like to know, then take a look at this on this website. Anyway, the matrix has a dimension of 18 by 18 elements, so it's quite large. But it will have exactly the same format like we have seen here. The only difference will be that it will be longer and it will contain more elements, but this will be there anyway because we are still considering the same motion. So what will happen at the end is that we are now able to make an estimate of, for example, the angles, even though we measure only the acceleration or the magnetic orientation or the signal from the gyroscope. And this is how it looks like, for example. So during this experiment, I had my board lying on the table. Then I have rotated that, so I have changed the yaw angle, and I tried not to move it in the other axis. So in the other axis I had the same orientation roughly, and then I tried to move it back to the original position. So I have rotated that only against the z-axis. And here you can see the result. This is the result from the Kalman filter that makes an estimation of the position. The dots here, that's actually the measured value. Well, measured means measured with acceleration and gyroscope, calculated based on the equations that we've seen previously. And the stars, that's the estimate of my Kalman filter. And you can see that it follows quite well. Here it begins, so I have constant position, constant angle, so you can see the dots are constant. But since my estimation of my Kalman filter needs to begin somewhere, I have set the initial estimate to 0. So my initial estimate of all values was somewhere here. And then after about 5 samples, the Kalman filter has adapted to that. And then about here, sample roughly 6, 7, I have moved the Arduino in a different orientation. So here is how I was moving it slowly. Here I kept a constant value for few samples, few seconds, and then I tried to move it back slowly to the original position. And we can see that here the Kalman filter follows quite well the values that it has measured. So it's able to adapt very well to the measured data. Now let me show you how did actually the MATLAB code change, and you will see that it did not change at all. At least the MATLAB code for the Kalman filter. So the code here, it's exactly the same like we've seen previously. So I have just added that here I measure the angles that I have obtained from the magnetometer and from the accelerometer, and here I have added the gyro. So this is the only difference, but I have made this difference because I measure something else. I measure more variables, but the main code here, this part and this part over here, that's exactly the same like we have seen in all previous examples. So if you put it like this, when it's like a matrix calculation, your algorithm stays exactly the same. The only thing that you need to do is you need to define correctly what will be the matrices. So you can see here my matrix is actually different from the previous one, and here also the matrix C is different. Now this matrix C is larger, and I've made the matrix C larger because by this matrix I'm telling the algorithm what variables do I actually measure in my calculation. So I recommend you to go through this algorithm so that you understand it. You have all examples in Moodle, and you just need to replace this part where you get the data from the serial line, for example with some constant or with some step change, to see how it reacts. And if you do run your algorithm and if you see how it works, I'm certain that you will understand that the Kalman filter is not that complicated. It's basically just a few equations that you need to run. Now let's extend the Kalman filter for another group of systems. Now, so far we have discussed systems that were linear. So they were described with a set of differential equations which had no sines and cosines, basically no nonlinear functions in it. But if you want to use the Kalman filter for a nonlinear system, then a normal Kalman filter will not work, because it is supposed to estimate the state of a linear system, and therefore if you have a nonlinear equation, it will not be able to make a correct estimation. Here I have an example of such a nonlinear system. So let's say we have a pendulum like this. We have some given length. We want to estimate the angle theta, and we measure this angle, but we measure this angle with some noise. So we have, for example, a sensor that's noisy, and based on this noisy data we want to make a clear estimate of the angle. So we will describe this with some differential equation which looks like this. We can see that this is a nonlinear equation, because here the angle theta depends on the sine of theta, and moreover this is like a really simplified equation, so it's without any damping. So what we are expecting is that if we start at some position like this, let's say initial theta will be something, then the pendulum will swing, and because we have no damping we will not lose any energy, so it will all the time swing between theta and minus theta on the other side. And that's what we see here on this chart. Now this example I have made it in Simulink. It's an example from MathWorks directly, and we will see what happens if we describe this system with such a nonlinear equation, and then we try to run a Kalman filter to make the estimation. If you are interested in how those equations are created, then you can go to this link and study that yourselves. So let's see in Simulink a demo how this will play. So again, you have the files available in Moodle. So here is the model of the pendulum. It's not only based on the differential equations. This is actually based on the mechanical objects that have some properties like inertia and so on. So it gives you quite a nice animation also how this pendulum is moving. Here we have the actual theta, the angle, the correct angle as it's coming from the model. And here we add some noise, so this measured theta, that's what we would get from the sensor. So the actual theta plus some noise, and then we feed this into the Kalman filter, and we will look on the output of this Kalman filter. Now let's make some initial assumptions. I will make an assumption that the initial theta of my pendulum is quite small, so let's say p divided by 18. So I will start from a small angle where the pendulum will begin, and I will also need to make an estimate for the Kalman filter what will be the initial state. So just to make it a little bit more complicated for the Kalman filter, let's not give it the correct estimate like p over 18 by, let's assume that it's p over 16, so that we have some difference between the estimation, between the initial estimation in the Kalman filter and here this actual angle. And what will happen now, if you look at this equation, you can see, okay, it's some constant times sine of theta. And from mathematics we know that if our angle theta is small, then approximately the value of sine theta corresponds to theta. So for small value of angle, I can modify this equation and I can remove the sine, so it will be just g over L times theta. But this approximation works only if we have small angle theta. So what we will see is that now if I run this example, I can see the motion here. This is the visualization. So you can see that the model is not simply a differential equation, but it contains actually the bodies and this lever and so on. And here we can see how the pendulum is moving. And we can see the estimation. So here is the estimation. You can see that now I have chosen a really big noise that we have on the sensor. So in the signal in red, that's the noisy signal, and here this sine wave shown in blue, that's the actual estimated value. And we can see that it looks nice because although we have a really noisy signal, here we have a nice sine wave, which is not changing the amplitude, so we have no damping and it's not changing the frequency. We could of course compare this with the actual value that we have estimated here with the actual theta. I will just decrease the noise a little bit here so that we have some other value of my noise. The way this code works is that you can calculate, you can set the parameters in the MATLAB. Here you can set the matrices A, B, C, and so on. So you can model a different system with different noise. Just let me now decrease the noise a little bit. So let's say about 1 order of magnitude, and we now rerun the code, and we should see that we have reduced the noise significantly. Now let's play a little bit with the code, and let's modify the actual angle where we begin our calculation. So let's begin, for example, not at pi divided by 18, but let's say pi over 2. So 90 degrees will be our angle. And let's still use this initial estimate like pi over 16. And let's see what happens. We will see that now the Kalman filter will not be able at all to make an estimation of my angle, simply because here the approximation that the theta is equal to sine theta is not valid anymore. So you can see that now here there is large difference actually between the measured angle and between the estimated angle, and the Kalman filter is not able to follow well the behavior of the system, because the behavior is non-linear. So what can we do about it? What can we use mathematically to improve this estimation? So what we can do is we can make a so-called extended Kalman filter. And the extended Kalman filter is modifying the way we are doing the calculation in the estimation. So for a linear filter, which from now I will call LKF, like linear Kalman filter, we have this state equation. And we can see that the new state is calculated based on the previous state times the matrix A, which describes the behavior, the dynamic behavior of the system, plus the matrix B times vector U, which is the control vector, so it's telling us what variables do we control, and this is the corresponding matrix. So if you imagine this in a graphical way, what are we doing? Let's say that here we have some variable x, and here on the x-axis we have the previous state, so this would be x on step I minus 1, and here would be the new state, so in step xa. So I have some initial state like this, and now I multiply it by some value. Of course, this is not an exact representation, but let's say I'm at this point and I would like to move to some other point. So let's say I would like to move to this point. So what happens is that I am moving in a linear fashion like this, because matrix A is constant, so I have a constant times the previous value. So what will this do graphically is that I will move from my initial estimate, which is this one, to the new state in a linear fashion. And this is the reason why for nonlinear systems will not work, because for nonlinear systems we don't have to move in a linear way like this between the new state and previous state. So what we need to do is that we need to modify this equation in such a way that this is not a linear equation, but it describes a function. And the function can look like this. So for example, I'm at some state x here, and if I want to move to a new value of state, which will be here, let's say this will be some delta x, and here I will have some increase in my value of my function. So we can see that at this point I have this increase. But for example, if I am at this point here and I make the same delta x here, then I would get a different value of my functional value. So what this means is that we need to describe somehow this function fx. And this function fx will be used in the state update equation. So we will not use the matrix A anymore, but we will use this function. So we see that this function tells us how to calculate the new state if I know the previous state, if I know the inputs, and if I know this function that relates the previous state and inputs to the new state. So this will be new in our calculation. And we can also have a nonlinear behavior on the output. So we will have another equation, another function h that will calculate the output based on some function and the state. Otherwise, the equations will be exactly the same. So if we are using the extended Kalman filter, the only two equations that we need to change is this state equation and then this output equation. So how to do it? How do I calculate this value of fx? Well, we can calculate this function quite simply if we use what's called a Jacobian here. And this is a matrix of partial derivations. So we will have some function fx that we will describe mathematically somehow. I will show you in a minute some example. And then we calculate partial derivations based on all variables. And by this we will create some matrix f. And what this means graphically is that let's say you have this point, and at this point you want to calculate what is the functional value of fx. So what you are doing by calculating the partial derivation is that you are trying to linearize the system around this point. So you're basically calculating the slope at this specific point. And then if I have the slope, I can take my slope, which is linear dependence. If I am changing, for example, by delta x here, and I know the slope, I can simply calculate what is the value of fx in this new point. And the beauty of this approach is that you can do it at every point. So for example, then when I am at this point, I can calculate the slope by calculating the partial derivatives. I have here my slope, then I can, if I have delta x here, I can calculate what is the new value of fx. So at the end, we will again obtain a linearized system, and we will again work with some matrix. But now we will not call the matrix A or B, but we will call it F here and H, because it is a different matrix than we had in the linear system. Now in the linear system, the matrix A and B did not change at all. It was constant for all times. But in this extended Kalman filter, at every step we are recalculating the value of the new matrix. So in both cases, in the case of F, we are saying how do we recalculate the new state based on the previous state. And the purpose of matrix H is to tell us, if I already have the state at the current step, how do I calculate the new output of my system. So the only difference in this sense between the linear Kalman filter and extended Kalman filter is that at every step I need to recalculate this matrix F and H, and this will kind of replace the constant matrix A and B that we have had in the linear case, but the equations will be the same. So let's take a look on how to actually use this in some example. So we will have our pendulum system. We can describe this with some differential equation, which you can see over here. Now we'll consider that this is a nonlinear equation without damping to make it easier. And if we describe this in state space, this is how it will look like. So x1 dot is x2, and x2 dot is directly my equation. So x2 dot is my angle theta that I see here on the chart. And we consider that we have some noise in our measurement. So we will see what will be the exact output from my system, and we will add some noise to it, and then we will feed this signal with noise to our Kalman filter to make an estimation. Now I have an example both in MATLAB and in Simulink. So let's see first the example in MATLAB, because here in MATLAB we can actually see what is the difference between the algorithm based on the linear Kalman filter and the extended Kalman filter. Again, you have this example in Muru. So what I'm doing here is that I'm solving exactly the differential equations so that I have an exact mathematical model. This is done in this section of my code. There is a help function that is solving numerically the differential equations, and the differential equations are described here. Then I take this exact solution and I add some random noise to the signal, and we can play with the amplitude of the random noise, and we can see if it has some effect or not. And then I'm calculating the Kalman filter here. This is the initial settings. I'm giving it some initial estimate. We can see again what effect this will have. And let me just skip that for the moment. And now this is the main algorithm from the Kalman filter. And I have kept on purpose also the comments that we had in the linear Kalman filter. So here I'm calculating the matrix F. I'm calculating the matrix of partial derivatives. I've made some function a little bit later that is doing that. So here this gives me matrix F. And then I'm using the matrix F to calculate the predicted process covariance matrix. So here instead, if we would have the linear Kalman case, linear Kalman filter, I don't need to calculate this. I would use directly the value A, and then in all those calculations the matrix A will be in place of matrix F, so in this equation. And then I'm calculating the Kalman gain, and here I'm updating the state with the new measured values. Now there are some more details that I will skip. If you are interested on why this is so, I suggest that you take a look on the example here on the demo of the Kalman filter. Where is it? It was somewhere. I think it was here. Here is the paper that describes how to actually set the values of the individual matrices. However, if I run this, we can see what will be the effect of the settings. So here we have the result. So in red here we have the actual value from the differential equation. So it's a nice sine wave. The measured signal is the black stars. So for example here, let me magnify it. So the black stars, that's the measured signal, and the blue symbol here, the blue star, is the estimated signal from the Kalman filter. So although we have some noise, the Kalman filter is quite able to follow the sine wave, and it will work even if I change the initial conditions for my Kalman filter. So let's say now that I keep the model as it is, but I will change the initial estimate of my Kalman filter. So for example, in my initial estimate I had that the angle starts at 90 degrees, and by chance here I had also that my model starts at 90 degrees. So I will keep the model at 90 degrees, and I will change my estimate here for the Kalman filter. So let's say I will start at 0. So on purpose I'm giving it the wrong estimate, so that I can see how fast will it be able to adapt to the real behavior of the system. So let's see what will happen. Okay, that's great, works fine. So we can see that here virtually no change at all. Here it's based on seconds. Maybe we'll see some difference at the beginning here. At the beginning, we are starting from somewhere from 0. Now I don't remember what is my sampling time. My sampling time is 10 milliseconds. So if I would like to see this this difference, I need to really magnify it, because now I don't see the beginning of my signal. So let's run it again, and let's just really magnify it around the origin. So let's say something like this, and even like this we can see, okay, now it virtually very quickly it will make the correct estimation of the behavior of the system. So with these settings, the Kalman filter works very well. Well, I've played a little bit with the settings so that it's very robust. So how do we actually calculate the Kalman filter? And here on this slide I will just compare the equations between the linear version, which will be on the right, and between the extended version, which will be on the left here. And I have summarized all the equations that we need in both cases. So this is like a complete equation list that you need to calculate the Kalman filter. So in the linear case, we see we have matrix A and B. In the extended Kalman filter version, we have this function, which is the partial derivative function. This equation is the same, except you see I have replaced the symbols of A to F, because now I'm using matrix F. The Kalman gain is the same, so that's the same equation. The update equation is exactly the same as well. And here this is also the same equation, except now here in the linear case I had that this h times xp, the prediction, this was a constant value, because I did not have any nonlinear dependence between the state and the outputs. But now I need to modify this again with some function. So this function h actually updates the output from my prediction. And that's it. That's the only difference between the LKF and the AKF. So you can code it exactly the same in MATLAB or in any other language. You just replace this line with some function that will calculate this matrix of partial derivatives, and then another function that calculates this. So it's once you understand what you are doing, then it's fairly easy to implement. And again, you have the codes available here in MATLAB, so you can just take the codes and you can play with the settings, and you can see what is it actually doing. So although it may look complicated, once you know what you are doing, it's actually not that much complicated. At the end, let me play a little bit with the settings of the matrix P, R, and Q. So we will see what is the dependence of the behavior of the filter on these settings. So how to actually set the initial values of those matrices. We know that this matrix R is the matrix, the covariance matrix that describes the behavior of my measurements. So how accurate is my sensor if there is some mutual correlation between the signals or not. So how to set it correctly? Well, you make an estimate of the uncertainties that you have in your measurements. So you make a diagonal matrix where on the diagonal you have the uncertainties of your sensors. And then you introduce something that I have called a tuning coefficient. And by tuning this coefficient, you can tune how sensitive your calculation will be to the noise, to the uncertainty that you have in the measurement. I have this in my MATLAB code, so let's take a look on how this is actually done. You can see that in my example here, I have said that I measure only one variable, one angle, and I have chosen this number. I have played a little bit with this number. This is basically saying what is the accuracy of my sensor. And you can see that in my code it's a constant number, so not that difficult to play with. Now let's take a look on the second matrix, which is the matrix P, and we know that matrix P is the process covariance matrix. So this describes us what is basically the noise in our estimation, if we have some rounding errors, if we have some dynamic behavior that is not described in the system, and so on. And one way how to make an estimate is that you estimate the upper and lower limit. So for example, let's say you measure temperature, and you know that you measure temperature in a room, and that the temperature in a room will be somewhere around 20 centigrades. So you say, fine, it will be somewhere around 20 centigrades. What can be the minimal and maximum value? So for example, minimum value will be 10 centigrades. This will be my lower limit, that's here. And maximum value will be, let's say, 30 centigrades. That will be the maximum value that's over here. And one of the approaches will calculate the average. So I take 30 centigrades minus 10 centigrades, which will give me 20, and then I set it to 0.5 of this value. So I will make an estimate that it's somewhere in the middle between the maximum and minimum value. And this is a fairly reasonable assumption. I usually can make an estimate of maximum value, minimum value, because I know something about the process. I know what do I measure, I know what value should it approximately have. And then I will use this in a matrix. So I will create a diagonal matrix where on the diagonal I have those estimates, those, let's say, average values that I have just estimated. So there is basically no problem to make an estimate for matrix P and for matrix R. However, it may be quite hard to make an estimate for the matrix Q. The matrix Q is the noise covariance matrix, and in order to make an estimate, we would need to know something about the noise. How does it behave? What property does it have? So there are some exact solutions how to do this. If you want to know some of them, you can take a look on this paper, for example. However, many authors use a trial error method to set the matrix Q. So you set it either as a constant matrix, or you just change it with some data that you have, and you see what is the behavior of your filter. So let's use this trivial approach, and let's use trial and error to set matrix Q. And I have matrix Q in my code as well. So matrix Q, where is it? Matrix Q is here. And one of the points why do we care about the matrix Q is that matrix Q has a huge impact on numerical stability, because we are calculating with a finite accuracy. Even if you're using doubles in a computer, you still have a limited accuracy of calculation. So the settings of matrix Q will have a huge impact on stability of your calculation of your algorithm. So right now I have this value, like it works. So if I run my algorithm, you can see it works quite well. But what will happen if I change it? So let's say, for example, I will increase the noise by 1 order of magnitude. This is noise in the calculation. So I don't know what will happen. So let's see if it will have no effect. No effect still. So let's say 3 orders of magnitude, for example, to see what will actually happen. Still nothing. Okay, so let's try other way around. So let's say -5, for example. I don't know why I did not try that. Okay, now you see that here I have made a wrong estimate about the noise. I have said, okay, my accuracy of the noise is really great, and here I have a completely wrong result. You can see that fine. Now some points are already completely out of my estimation, although some of them are still there. So if you make an estimate that your calculation is really accurate, this will have an impact on numerical stability of your algorithm. So let's say even more. So let's say another 1 order of magnitude, and you can see that now I have more points that are really just nonsense, because I start with the pendulum at 90 degrees, and here this is really the numerical stability. It's one sample outside and then it comes back. So this is telling me that I cannot set the value of Q to 0, because this is telling me I don't have any noise at all in my calculation, which is definitely not true. Plus, the matrix Q has an effect on the description of the system. If I add some noise on the system, I'm telling the algorithm that the description of the system is not accurate. So I have some values that I do not measure, I have some behavior that I do not measure, and so on. So if I would set Q to 0, I'm saying my model is exact, and I don't care at all about any noise that I have in the system. So I cannot send this to 0. So we have done this by trial and error. If you want to see an exact approach, then for example this paper gives you a quite good description. So to summarize, we have studied the Kalman filter in 2 versions, for linear and for nonlinear systems. We know now how to use it, how to code it in MATLAB. You have the code available. If you want to see let's say more details about the Kalman filter, here I have a few recommended sources, mostly some research papers based on that, but also some tutorials. So I recommend you to take a look on the tutorials if someday you would like to implement the Kalman filter. Here there is such an example of a Kalman filter, an interactive tutorial. There is a really great series of videos on YouTube about Kalman filter. Here I forgot to translate that in English. So this series of tutorials, you can see that they have 55 parts related to Kalman filter, and each video is, let's say, between 5 to 15 minutes, so roughly. So you can see that we could really spend probably the whole semester in talking about Kalman filtering. I think it may come useful if you are building some control system, if you want to control a system like a drone, for example, or a robot that has noisy signals. So the Kalman filter works quite well in all those applications. So this is a recommendation what you could watch if you will be interested into knowing more details about the topic. And again, more videos about the extended Kalman filter and about how to use it in Simulink. You have the simulating examples also available in Moodle, so you can run it and you can see what is the behavior of the system. The last topic that I would like to cover in the sensor fusion part is one example of sensor fusion for image signals. Of course, there are more algorithms like this, but I want just to show this as a demo to show you that it's possible. It's not very difficult to understand how this algorithm works. And in next year, you have a specialized class that's devoted for signal and image processing. So we will learn more algorithms in the next year. So the one algorithm that I would like to show you is an algorithm that allows you to estimate a distance of an object if you have two separate images from two cameras. So let's say you want to solve a problem like this. You have a car, and the car needs to see the obstacles in front of the car, and needs to make an estimation how far those obstacles are. So this is my obstacle. This is another car in front of me, and this is my car, and in my car I have two cameras. I have camera 1 and I have camera 2. Both cameras will see the same image, so they see the car. But if you have a signal, if you have a picture only from one camera, you cannot make a calculation what is the distance. So I'm looking for an estimate of distance h. And with one camera I cannot do it, because with one camera I don't have enough info to calculate the distance. But if I combine somehow with some algorithm the two images together, I can calculate what is the distance h. And for this I will need to have pictures from two cameras that are taking the picture of the same scene, but they have some defined distance and they see the scene slightly different. It's exactly the same like we humans see, and we can get the distance if we see the object with two eyes, because the two images are slightly shifted, and this will be the principle behind this algorithm. So let's take a look on how we can do it. So let's say I have a scene like this. This is a view from the top. So I have a camera 1, and here I have camera 2. And I have two objects, just to make it simple. So I have a red ball, and I have a blue cube here. So if we now look on the images that we see from the cameras. So for example, camera C1 here, you can see, okay, fine, it will see the red circle and it will see the blue rectangle, but since it's the pointer, and so it has a field of view, let's say like this, and here if I make a line like that, you see that the red circle will be quite close to the blue rectangle. So what camera C1 will see is roughly something like this. I see the circle, the red ball, and I see my cube here, and they are quite close together. The camera 2 will see something different. It still sees the same scene, but it will have a different arrangement of the objects. Let's say this is my field of view like that, and now I will see the red circle, a larger distance between the red circle and the blue rectangle, and then nothing. So this is what I see. I see the red ball, and here I can see the blue cube. And we can see that this distance between the objects is different than it was here. So here it's larger and here it's smaller. Now, for the calculation and in order to make it simple, I will assume that both images are vertically aligned. So this means that this coordinate, so for example, if this would be, let's say this would be x and this would be y direction, so that the coordinate where my ball begins here is the same in this picture and as this picture. So this is the assumption of my algorithm, otherwise it would not work properly. So you need to manually or mechanically adjust this position so that really you have an aligned picture. Of course you can do it in software, but this adds an extra step, and I wanted to avoid this problem here. So I'm assuming that now I have aligned images in the vertical direction. So now let's take a look on a more complicated image. So let's say I have a picture like this. This is the picture only from one, this is a picture from the left camera, and this is the picture from the right camera. And I'm assuming still that I have the pictures that are vertically aligned. So whenever there is a feature, for example the tip of, let's say for example this let's say this cone here, then it will have the same y coordinate also in the second picture. So this coordinate is the same. And now I can use an algorithm that will search through the image and will tell me what is the shift between the different features. So how is this working? I will select some region of my picture. So let's say I will select for example this region, and in this region we can see that I have a tip of the red cone, which is over here. And now I know that the picture is vertically aligned. So I only need to go left or to the right, and I need to search for the same feature, and I need to look what is the shift between this position where it originally was and the new position where it's right now. If you try this with your eyes, if you close one eye and then the other one, you'll find that the movement will be always to the right side here. So if this is my picture from the left eye, if I close the left eye and look only through the right eye, this will be always shifted to the right. So I only need to start from my position over here, and I need to look for features that will be the same or similar, but it will be shifted to the right. And the value that I'm looking for is the shift. So let's say I start with this coordinate, let's call it x, for example x1, and then I'm looking for the coordinate x2, and I'm looking for the difference. So if this is shifted further to the right, it means it has a different distance than if it is shifted to less. So for example, if I find the feature will be here, this position, it has a different distance than if it is here, like that. This algorithm is called block matching, and it is assuming that the pictures are aligned in this direction, so that otherwise it would not work. So so this shouldn't be well, it is fine. Horizontally means in this direction that it's aligned. So we need to search the image for the most similar block. And how to do it? Well, we take this as a matrix. We will subtract the other matrix over here, and we will calculate the difference. And since we are looking for the absolute difference, we don't care if it's positive or negative, we will calculate the absolute difference. So this is called a sum of absolute differences. And I will repeat that. Every time I will run it in a loop, I will shift it by 1 pixel to the right. I will calculate it again. So I will go through all this, like that, through all this region. And then I will find for which value, for which position x2, I have the minimal absolute difference. So minimal absolute difference means that it's similar to my original block in the left picture. So what will be the result? Here I have some calculation results. By the way, it's another example of MATLAB directly, so you can find it in your MATLABs, or you can download it from some website. I have a link. In the MATLAB code. It is clear that this will depend on the size of your window here. So if you make a larger window, you will cover larger area. So for example, like this. So larger area means that you will have let's say less ability to distinguish the details, because you are comparing this whole area with this whole area on the second picture. So if you choose a large area, it will act like a filter that will filter out the details of your image. But on the other hand, if you take a smaller picture, you will have more noise, because if you take a smaller picture and you're comparing like less numbers with let's say for example 3 by 3 matrix, and then the sum of absolute differences will be more noisy, and this is the outcome. So the left result, the left chart is if you have a block size of 5, so 5 pixels by 5 pixels, so you have a matrix that looks like this, and here you have is it 5, 1, 2, 3, 4, 5, yes, so 5 by 5, something like this, and another one. So this will be your picture, so matrix of 5 points by 5 points. So here we can see that I have more noise in the picture, but less detail. And here I have tried the same pictures, exactly the same settings, with block size 10. So you have 10 by 10 matrix, so it's 4 times larger than this one. And you can see that we have less detail, but we have less noise. So we have like a better filtering ability to filter out individual noise. It's still not perfect. You can see that here we have a lot of noise, and it's probably not the best algorithm still, but anyway, it can give us an estimate that the cones in front are closer than the cones in the back. And that's what we see here as humans. We know that those cones are closer, and those cones at the back are further away. But if you want to evaluate the distance with an automatic algorithm, you just need some way how to tell it from this image. We as humans, we have it kind of embedded in our brain that this is closer and this is further. So let's try this now in MATLAB. I have well, you have the code in Moodle again, so I think it should run. If it will not run, then it's probably that I forgot to upload to Moodle those two images with the codes. So if they are not there, I will upload them after the lecture. I think I've uploaded them last week. So let's see the algorithm. It is based on some ideas from this website. So I'm definitely not the author of the algorithm. I just implemented the way it is working, and it is searching for the algorithm. So what I'm doing is that I first read in the two images. They will be stored as a matrix in MATLAB. The algorithm, I did not mention that, the algorithm, in order to make it work, needs to have black and white images. So it's not working with the color in the image. So the second step that I'm doing is that I convert this to black and white. And this is here the function that converts to black and white. Let me just run it so that we see the black and white result. So here is the two pictures, black and white version, left and right picture. I don't know how this could be magnified, so maybe this is better. This is the original image that I have loaded from the file, so left picture and right picture. And here is a little bonus. If at home you have some goggles with green and red glass, if you look at this, you would see this picture like in 3D. So it's like an example of how to create a 3D picture. And here we can see nicely what is the shift between the two images. So here one cone is the same cone like this one. So the one cone is here in one picture, and the other eye sees this like that. So it sees it with some shift. And you can see that it's really aligned in this direction. So the tip of the cone here is the same here. The tip of this, for example, this cone is the same like this one. And here we can see the difference in distance. So here, this object, we know that it's farther away, and we see that the difference in distance is smaller. And here, the two cones are closer, so we see that this distance is larger. Sorry, this is closer to us because this distance is larger. And this is what we will find in the algorithm. So if I run that, we will get this result like this, and you can again play with the block size, and you can see what effect will it have on the calculation. It has not only an effect on the noise that you have in the algorithm, but it has also a huge effect on the speed of your algorithm. So let me run it, and now I will not hide this command window in MATLAB, and we'll see how long will it take to calculate the actual image. At least on my computer, it's too slow to process in real time, and the images are fairly small. You can see here my images are about 375 points times 450 points. My initial idea when I was creating this code was to run it in real time to show you what is happening with my web camera, but it turned out that it takes like, I don't know, 5 maybe 10 minutes to process one image. So I came back to the MATLAB pictures, which have a fairly small resolution. So let's run it, and let's now see in the command window how is the calculation going on. In this calculation, this particular example, I have selected that the block size is 10 pixels, and that I'm looking only for 50 pixels to the right and nothing more. You can see, okay, it's not very fast, but will take maybe 30 seconds to process one image, so it's, well, at least the way it's written, it's fairly slow. And here I can see my result. For some reason I have now a wrong scale in my picture here, but we can see that we have different colors here. We have this is closer to us and this is farther, so it is able to find it. Now the problem is that somewhere in my chart here I have disabled the automatic scaling here in the color axis, and I would need to search where that is. But let me change now the number of pixels in my block. Let me change it to 5. So we will have a smaller square where we are searching. And what will this do is that now we'll have a different time because we are calculating different number of values. So previously we had like 32 seconds, I believe, and now let's see what will be the change in speed. So I expect something different than 32 seconds. And we will also see, well, 28, so it's a little bit faster with a smaller block. And here we can definitely see that we have more noise in our picture. So it's less clear where the object is and how far is it from us. So here is a trade-off between the block size, the speed of the calculation, and also we're handling with image signals, so of course there will be a huge influence due to lighting and so on. So I will not go through this MATLAB code. You can take a look on your own on this tutorial. It explains quite well how it works. It explains also how the code is working, and this example you have available in Moodle. So that's all for the sensor fusion part, and next week we'll have 2 more lectures to go. So next week we will focus on algorithms that are used to validate our signals from the sensors.